Hello everyone, thank you for attending and showing interest for this session. I am Abdulkadir. Recently I have received my PhD degree from Institute for Communication Systems, home to the 5G and 6G Innovation Center at the University of Sojourn. Today I would like to present our paper on profiling vehicles for improved small cell beam vehicle pairing using multi-amp Bandit. Before starting my presentation, I would like to thank the co-authors Dr. Fo, Dr. Heong, and Professor Klaus for their valuable contribution to this work. I would like to also mention this work partly supported by Horizon 2020 research program in Project 5G Heart and dedicated 6G project. Here is the outline. First, I'm going to talk about the motivation behind this work in section 1. Then I describe the considered scenario and problem formulation for beam selection in section 2. This brings me to explain the proposed context-aware multi-amp Bandit learning design. The performance validation are explained in section 4, and then finally I draw my conclusion in section 5. 5G technology has tapped into millimeter wave spectrum to create additional bandwidth for improved network capacity. In this regard, the use of millimeter wave for specific applications, including vehicular networks, has widely discussed. However, applying millimeter wave to the vehicular networks faces challenges of high mobility nodes and narrow coverage along the millimeter wave beams. These factors lead to a short period of sojourn time, which in turn causes frequent handovers and high overhead. Traditional approach of choosing a beam that can achieve the strongest SNR may lead to a vehicle to move out of the beam quickly due to local street layout. Thus, a different strategy is needed for the beam selection in vehicular network applications. We propose profiling vehicle mobility for a machine learning agent to learn the performance of serving vehicles with different mobility profiles and utilize the past experiences to select the appropriate millimeter wave beams for service. Let me introduce the scenario setup. Figure on the right illustrates our scenario setting using OpenStreetMap and our mobility simulators. The millimeter wave small cell is located near Guildford Town Centre in the UK. It has 6 antennas, each faces different direction to cover the entire surrounding. Each antenna may consist of a set of antenna elements, creating a beam at a direction. With 2 RF chains at one time, it can only activate 2 beams to serve the 2 vehicles. The shaded areas in the figure demonstrates 2 active beams serving 2 vehicles at that particular instance. Following the millimeter wave beamforming model used in reference 2, the beamforming gain of antenna is calculated based on this formula. Here, B3dB is the 3dB beam width, which is set to 35 degrees for considering 6-sector case. Delta theta is off-center angle, which is the angle between the beam center direction and pointing direction to the serving vehicle. While the base station has antennas with fixed pointing direction, we assume that the vehicles have steerable beam antennas that can track and steer towards the base station during the communication. Eta here is the constant value of 12. And the SNR of serving vehicle is computed as follow. Here the path loss is following the 3GPP urban micro is given as with this formula. And P0 here is the beam transmit power. And GTX and GRX is the transmitter and receiver antennas gain. N is the noise, including the thermal and noise figure, and D is the distance between the transmitter and receiver. To maximize data transmission between the small cell and serving vehicles, the radio resource allocation strategy for this setup shall aim at serving vehicles that have the longest sojourn time within a beam. Considering fixed data rate, the beta transmission rate of the beam I at time t is obtained by this indicator function. If a beam I is serving, then the beta would be R, otherwise it's 0. Otherwise, it's because of the user is performing handoff procedure, so it means that waiting for data to be routed from the macro base station, or it might be inactive or no vehicle within this beam sector to serve. To remind also that each handover event incurs blockout or out time, resulting transmission beta to be 0. By increasing the vehicle sojourn time, we can minimize the handover frequency, hence maximizing overall rate. In multi-amp Bandit, there is an agent who is trying to maximize its rewards by pulling set of arms. In our scenario, the millimeter wave base station acts as agent who is trying to maximize the reward by activating set of beams. We apply both traditional multi-amp Bandit and contextual multi-amp Bandit. Given that our objective is to select vehicles with the longest sojourn time within a beam, the reward is the connection duration experienced by a served vehicle. Different from the traditional multi-amp Bandit, we have context in contextual multi-amp Bandit, which is vehicle mobility information. We notice that the context describing vehicle mobility feature also implicitly encapsulated the information of local street layout. So considering set of context and beam pair, rewards becomes like this. Before showing the numerical results, I would like to demonstrate mobility simulation in Python we developed to simulate vehicular mobility and various algorithms. The animation shown here is captured during the exploration period, where the base station begins by randomly selecting the vehicles to serve. Vehicles passes through the town area, and some vehicles chooses to enter the town center and park in a car park. The sectors are shown illustrative coverage. The actual beam coverage is based on beam forming and channel models. In our simulation, there are hundreds of vehicles continuously moving on the map. We simulate 10 hours of operation, where the base station begins full exploration for learning. Then it switches to full exploitation after 3 hours, which is the 30% of simulation time. As measure, we focus on average beam sojourn time, which is shown on this figure for different algorithms. At the beginning, both multi-amp Bandit and contextual multi-amp Bandit performs similarly to the random selection scheme due to full exploration in the first 30% of the simulation duration. After switching to exploitation, contextual multi-amp Bandit doubles mean beam sojourn time when comparing to that of random selection scheme. It also outperforms classical multi-amp Bandit by 40%. Interestingly, we see that the performance of best SNR equals the lowest among all. This is mainly due to unfavorable street layout for best SNR scheme, which try to select the strongest signals, which means that the closer user, hence there is an short beam sojourn time. This also shows that the importance of knowing the local street layout for base station to operate efficiently in V2X application. To understand the benefit of profiling vehicles, we show the breakdown of the average beam sojourn time for each beam in these figures. With multi-amp Bandit, beam 1 performs poorly due to its shortest sojourn time. during the learning phase. Thus, in exploitation phase, the base station avoids utilizing beam 1. This poor performance can be understood easily by inspecting the local street layout presented in map. We see that most vehicles moving on the main road in east-west movement only remain briefly in beam 1. Thus, the beam sojourn time is very short. Some vehicles moving on the main road in beam 1 in south-north movement may have longer sojourn time, but since the Maltian Bandit do not differentiate between these two, the resultant average sojourn time remains low. Focusing on beam 1 in contextual Maltian Bandit algorithm, since context is explicitly used, context Maltian Bandit is able to differentiate between these different moving directions. So the contextual Maltian Bandit utilizes a wider range of beams than Maltian Bandit. As a conclusion, we can say that utilizing the vehicle mobility information to decide which beam to activate to serve a specific vehicle, we proposed applying Maltian Bandit learning models to learn from past experiences. We applied both traditional Maltian Bandit and contextual Maltian Bandit. For contextual Maltian Bandit, we explicitly use mobility information as the context. We found that the vehicle moving direction and its distance from the small cell are sufficient to avoid selecting short beam sojourn time. Aiming for longer beam sojourn time, our results confirm that using mobility information as context in contextual Maltian Bandit model outperform classical Maltian Bandit, best SNR, and random beam selection algorithms. This brings me to end of my presentation. Thank you for your patience. If you have any question, please feel free to contact me.